time slot that, like everyone is a little bit unhappy. So people in West Coast are unhappy that it's too early. People on East Coast, it's the middle of the lunch. People in Europe, it's too late. But nevertheless, we have all really exciting, great talks here, and we have really great speakers. So I hope that that will make us all happier to listen such a excited talk. So who we have today is Gethin, and you probably all know Gethin Norman because of the Prism tool and all his work that he did on probabilistic reasoning and probabilistic model checking. But when I was looking at his biography, I noticed that he was also behind many awards that are on the topic of verification on randomized and stochastic systems. And what I found very impressive is that all of them were rated outstanding upon their completion, so which I think it's really great. He is right now a senior lecturer at University of Glasgow, but he finished his PhD in Birmingham, and I'm looking forward to his talk. So please, the floor is yours.
Okay,
or the Zoom is yours.
Yes, let me just share my screen. Okay, so
so maybe, excuse me, just one question. Do you want to have interactive? So is it okay if I will just scan if there are some questions and then we'll ask you, or would you like to take questions after the talk?
No, I'm fine to be interrupted, but if you just tell me, because it's hard to notice.
I will pay attention for the Zoom chat.
Great.
Okay, thank you.
Okay, so this talk is about verification and control of partially observable probabilistic systems. So just to put it into context with the videos that I prepared. So I prepared a the videos into three parts. There was a first part which just gave you an introduction into probabilistic systems and the formal verification of them, why we actually do this. Then there were two main parts to the videos. The first was on discrete time Markov chains. So here these are probabilistic systems in a discrete time where there's just discrete probability, and I went into those. I defined paths and probabilities, and explained how to compute both probabilistic reachability and expected reachability properties. And then I also explained how these can be used for computing the probability of satisfying LTL and automata-based properties. And then I went on to Markov decision processes. So here these are discrete time Markov chains, but you also add in non-deterministic behavior. And I went through a similar process for those, defining probabilistic reachability and showing how that can be used for more general LTL and automata-based properties. So in this third part, what I'm going to talk about are partially observable probabilistic systems, and I'll include a recap of what you need to know from the videos. So if you haven't watched them, that is not an issue. Okay, so I'll start just by giving a bit of a motivation. So often when we want to guarantee the correctness of complex systems, we need to take into account quantitative aspects, and this includes probabilities. So this could be due to failure rates or uncertainty, due to the sensors that we're using, but there's also timing characteristics. And good examples of this are in communication and security protocols, where in order for them to work, they have to have certain timing or delays. So in order to show they are correct, you need to incorporate that into the model. Now, a further complication is that we often also need our non-determinism. So this is where we don't know how the system is going to behave. So there might be one or two or several different options, and we can't assign or it doesn't make sense to assign a probability to them. So examples of this is, it could be the input instructions from some external entity, such as a controller, and it's also we need non-determinism when we're modeling both concurrency and abstraction. Okay, now having these three things, we've done it in the past. We've shown that we've got automated verification techniques that have been successfully used to analyze quantitative properties of systems that have probability, timing, characteristics, and non-determinism. And two classical models that we've used are Markov decision processes, where there's a discrete model of time, and probabilistic time automata, where there's a dense or real model of time. And we've also got extensions where we've add more than one choice of more than one aspect of non-determinism, and there we move on to games. And we've done some recent work on concurrent stochastic games. Now there's two dual problems. One is the verification, and that's proving that some formally specified property holds, or finding the optimal or minimum or maximum value of some property. And there's the dual problem is to synthesize the controller or other strategy. So that's how the non-determinism are resolved in order to guarantee the value of some specified property. Now, one thing that this hasn't taken into our consideration is the extent to which the system state is observable to the entity that are controlling it. So, for example, if you think about our security, our protocol, then if we're trying to model the attacker, then it can't see the data that it's trying to find out about. If it could see the data, then obviously it knows what it is. So it shouldn't be able to observe it when it's making its choices or trying to attack other system. So also, if you think about a robot that is in some environment, it can't see the whole environment. It can only use its sensors, so it's only got a partial view of the world in order to make our decision. So if we're going to model that, then in other model, then we also need to model the fact that the robot has only a partial view of other world. And there's also a more a third example is routing our packets. And this is a concrete example. So here, when a scheduler is choosing how to route other packets, then it can't look at other channel state, because if it does that, then it will add in extra costs and delays, which will cause issues. So that's three examples just to show that we need to take into account what the controller can observe. So this leads us on to partially observable MDPs, or more shortly, POMDPs, and this is a natural way to extend MDPs so that we can take into account this partial observability in our discrete time case. So one thing to say from the start, the analysis of POMDPs is much more difficult than MDPs, and key problems are undecidable. So that means that we can only get approximate results. Now, I should say that the use of POMDPs is common in AI and planning, but they're more interested in our discounted or finite horizon problems where things are decidable. while in a verification, it's normally the case that we're not interested in such properties. We're more interested in, can we actually get to a certain state, and the time that it takes is not as important. So there's been limited progress in the practical techniques in this area, and in this talk I will address some of these issues. So what I'm going to introduce is techniques for the verification and our control. So both the verification and the strategy are synthesis of partially observable probabilistic systems, both under discrete and dense models of time. Okay, and as I said, the problems are undecidable, so we are looking at approximate analysis, and we'll first do approximate analysis for finite state MDPs, where there's a discrete model of time. So we'll give upper and lower bounds for the property of interest, and here the properties are the minimum and maximum probability of reaching targets, or the minimum or maximum expected cumulative reward before we reach some target. And these are the fundamental properties in probabilistic model checking. And we'll also show how to synthesize optimal controllers or our strategies. And if our upper bounds are not close enough, then we can also refine and then try and get better bounds. But we can't guarantee that the bounds would be better, as it's undecidable. And obviously, if we know that we're going to get better answers, that would mean that we could decide our problem. Okay, and that's the first part, which is on a discrete model of time, and then in the second part, I'll move on to partially observable probabilistic timed automata. So here these are probabilistic timed automata extended to have partial observability, and our semantics then yields a uncountable infinite state MDP, which is obviously even harder to solve, but here we'll show that you can use what's called a digital clocks discretization, and this reduces the analysis to a finite state of MDP, and then I can use the same techniques as for the finite state of MDPs. Okay, so as a outline, I'll first go over MDPs, then I'll go on to MDPs. We'll have a short break, and then I'll go on to probabilistic timed automata and the partial observable probabilistic timed automata. And then I'll just mention something on the implementation and give you some our conclusions. Okay, so first, what is a Markov decision process? Okay, so this is a model that it's, first of all, it's in a discrete time, and it has non-deterministic and probabilistic behavior. So it's a tuple of this form. So first of all, we've got a set of states, or the state space, and we've got some state S, 0 that we start in, and we've got some action alphabet A. So these are I'm in some state, and then I can perform some subset of actions. Next, we've got what is the partial probabilistic transition relation. So here, given any state and action, this function might be defined. If it is, then that means that that action can be performed in that state. And if it is defined, then this gives us a distribution. So that tells us what the next state will be with what probability. And then the final part is a reward function that says that if I'm in a state and I perform an action, what is the reward that is accumulated. So here is an example MDP. So we've got the states, the actions are labeling our transitions, and so are our rewards. So let's give an example. Okay, so in each state S, there is a non-deterministic choice. So what action do I perform next? And this is over the actions for which the distribution is, the probability transition distribution is defined. And if we choose action A, then we'll move to state T with this probability here. So here, if we look at state S1, we've got two actions that are available, B and C. If we perform B, then we'll either go to state S0 with probability 0.7, or we'll stay in S1 with probability 0.3. And if we do choose B, then we accumulate the reward 1.3. On the other hand, if we've chosen action C, then we'll either go to S2 or S3, each with probability 0.5, and we will accumulate the reward to 2.8. Okay, so from this, we can then say what paths are in an MDP. So this is just a sequence of states and actions. So you're in a state, you choose an action. So we need this to be defined for each SI and AI, so we can actually do that action. And then the next state, we have to get here with probability greater than 0. So in each case, the probability, if I'm in state I and I choose action AI, then the probability that I move to state SI plus 1 must be greater than 0. So if we think of a path, then it both resolves the probabilistic and the non-deterministic choices. So we choose both the action, which is resolving the non-deterministic choice, and then we choose the following successor state, so that then also resolves the non-deterministic choice. Now, if we just consider our strategy, which is also called either a scheduler or a controller or a adversary, but I'll stick to strategy. So here, this is a resolution of the non-determinism only. So how does this work? So given a finite path or history, then the strategy says, what action do I do on next? So it just, given any path, it will return what action is performed. And then if we're under our strategy, then the behavior of an MDP is fully probabilistic. Okay, so it actually gives you a discrete time Markov chain. And if we've got our strategy, then we can reason about the probability of events over paths. So if we've got our strategy, then we can talk about what's the probability of a path reaching a certain goal set. Okay, so the two properties that I'm going to consider are probabilistic and expected reachability, and these are the fundamental to concepts in quantitative verification. So all the sort of LTL and automata-based properties involve some sort of graph-based analysis, and then reduced to some form of computing optimal reachability of values. So if we've got our strategy, then we've got our DTMC, and we can talk about what's the probability of reaching some target T under a strategy or sigma. And similarly, we can talk about what's the expected reward that is accumulated before we reach a like target set T under the strategy R sigma. However, we've got a sort of there's a like infinite number of strategies. So what we consider is like the optimal, which can either be like the minimum or the maximum like value over all like possible R strategies. And as I said, this is it's like fundamental. So just from this, we can then do automata based and also other like reward based properties. And just to say that there are efficient algorithms and tool support for this. And for example, Prism uses value iteration for our computation, and we can compute both the optimal value and also a optimal strategy. So this is our strategy under which we achieve the optimal value. And just to say that that we can return a optimal strategy that picks a action in each state with our probability 1, and it doesn't need to look at the history. So it's memoryless. It can just base its choice on the sort of final state of the path. So given any two paths that end in the same state, it would make the same choice for those two paths. So there's much more detail on this in the video lectures for parts 1 and parts 2. So there's one more thing that we need on MDPs. So this again is in other videos. So here, how do we actually compute these values? So this is the case for expected reachability. So if you've got some value or function that goes from the states to the reals, then to compute the optimal expected reachability of values, we can just repeatedly compute these. So this is a recursive. So the value in state S is dependent on that in state T. So how does this work? Okay, so first, if we're in some state that is in the target, then we've reached the target, and we're not going to accumulate any reward. So the reward is 0. And if we haven't reached the target, then we can look for each action. We've got the reward that we accumulate when we perform that action. So we're in state S, so we perform action A. So this is the reward that we accumulate. Then if we make our transition to state T, then this is the probability that we move to T, because we were in S and we performed A. And then this is the expected reward from state T. And if we sum over all T, then this gives the expected value under the assumption that we perform A in S. So since we do this for each action, and we want the optimal, then we either take the min or the max of like this. So if we do this, then under certain restrictions, which I won't go into here, then if we just keep doing this, then this will converge to the optimal expected reachability values for all states. And the case for probabilistic reachability is almost the same. So in this case, if we reach if we're in our target, then obviously we reach it with our probability 1. So this would be 1, and then we just don't have this part here, as we're only interested in probabilities. Okay, so that's MDPs. So now let's go on to our POMDPs. So these are MDPs but they are extended by restricting the extent to which the current state can be observed by our strategy, and so that can change, influence the choices that it can make. So there's several different notions of what can be observed. So I've chosen the simplest, but most are equivalent. So if you can use one form, then you can rewrite the POMDP to use the other form of observability. So what is a POMDP? Well, it's a tuple similar to an MDP. So we still have this. So we have the first lot of elements are the same as we have in an MDP. So we've got a state space, we've got an initial state, we've got a set of actions, we've got the probabilistic transition, our relation, which is again partial, and we've got the reward function. So given a state and action, it tells you what is the reward that is accumulated. And what is added in is we've got this set O of, which is a finite set of observations, and then we have this function that says, if I'm in state S, which of the observations do I see? Okay, so now our strategy doesn't see a state, it only sees what is observable. So this is applying this observation function to our state. So there's one technical requirement, and that says that for observationally equivalent states, the same actions must be available. So this is, so for any states S and S prime, what is observable has to be the same if they have the same set of actions. So why is this? Well, if the action set are different, then the strategy could see that two different action sets were available, and then obviously it would be able to tell you that the states weren't the same, because you could do different things in those two states. So for POMDPs, for paths and strategies, they just carry over directly. There isn't anything that changes for paths and strategies. However, there is a restriction on the class of strategies that are used for POMDPs, and the class that are used are what are called observation-based strategies. So these must make the same choices if it's observed the same thing, because as far as the strategy are concerned, it's in the same place because it is observed the same thing. So there could be two paths. If they're observationally equivalent, then it has to do the same thing. So what does it mean to be observationally equivalent? So if we've got two paths, pi and pi prime, then they're observationally equivalent if each of the states yields the same observation, and each of the actions is also the same. So under our requirement, that means that any observation-based strategy would have to make the same choice in pi and pi prime, because it would have observed the same thing. So just to say that that we can find or we can look for optimal our strategies for probabilistic and expected reachability for our POMDPs, but now they need to know they're no longer memoryless, as they need to look at the history as what they've now observed in the past can give them information as to what state they currently think they are in, as we will see. But they're still are deterministic, so they still only there's no need for a randomization. So let's just give a simple example just to see what is going on. So this is a maze. So say that a robot was randomly placed into one of these grids, and then tried to reach the target or location, let's say, which I've colored in red here. So so it's in one of these grids, and it can try and move in 4 different, or it can try to move in 4 different directions. But obviously, for example, if it was in grid 1, it could only go either east or west. Now, all that the robot can see is the walls that are surrounded it. So it doesn't know that I'm in grid 5 or I'm in grid 8. All that it knows is that I'm in a grid square and there's a wall. So here, if I was in 5 or 8, then all that I could see was there was a wall to the east and to the west, and there was no wall either to the north or to the south. So it wouldn't be able to tell if it was in state 5, 6, 7, 8, 9, or 10. So if it was placed in either of these are squares, then it wouldn't know where it was. So if it was going to try to get to the goal, then it wouldn't know if it was in either of these. So obviously, if it was in, for example, if it was in 5, then it's best to move up. While if it was in 6, it would be better to move down because you're getting closer to the goal. But if it was randomly placed in the grid, then there's a higher chance that it's either in 5 or 7. So the optimal thing is to move up. So even though in state 6, it would be better to move down, it doesn't know that. It only knows that it's in one of these 6 states. Now, if it moved up, then it would see these 2 walls here, and it would now know that it was in state R0, and that it could now go directly to the goal. Similarly, if it was in 6, then it would move up to 2, and this is the only grid square with just a wall to the north, so it would know that it was in 2, so it would then go backwards and head to the goal. So this is, I've already said, so it turns out that the optimal time to optimal or minimum number of steps to reach the target is 5.23, and this is for a strategy of POMDP. Now, if we were to turn it into a MDP, which meant that the robot could always see where it was, then the optimal number of steps decreases to 4.0, and we will come back to this. Okay, so how can we compute these the optimal reachability values for POMDPs? So as I previously said, these problems are actually are decidable. So this means that we can't really think that we're going to be able to compute exact solutions. Now, a useful construct is what's called a belief MDP. So this is a fully observable MDP, which has the same optimal, probabilistic, and expected reachability values as our POMDP. However, this comes at a cost. So it's we don't just get to move to a finite state MDP, which has the same values, as then it would be easy to compute the values of the POMDP. So this has to come at a cost, and this comes at the cost that the MDP that we go to has a continuous and countable state space. And the states are what are called beliefs. So these are probability distributions over the state space of the original POMDP. So the intuition here is in a POMDP, we may not know what state we are in. However, we have observed certain things as we've moved through as we've performed actions, and so we also know the structure of the POMDP. So as we observe things, we can determine the likelihood of which state we are in, and we update this as we change state. So let's see how we can use this to construct some certain probabilities in this belief MDP. So let's say that we're in some our belief B. So this is our distribution over the states that we could be in, and there's some observation O and action A. Okay, let me just so first of all, let's look at if we're in our belief B, and what's the probability that we observe O after performing the action A in B. So this is given by our formula here. So why does this work? First of all, let's look at this here. So this is so say that we were in state S and we perform A, then this is the probability that we reach T. So if we do the summation over all states that have the observation O, then this gives us the probability of observing O from S when we perform A. So if we're in S and we perform A, then this is the probability that we reach T. So we just sum over all the T where we observe O. And then this is the belief that we were in. So this is B. So this is the probability that we're actually in S. And then we sum over all the states that we could have been in when we perform A. So this indeed gives us the probability of observing O after performing action A in our belief B. Okay, so that's the first part. So the second part, so say that we were in B, we perform A and we observe O. What then is how do we update our belief? Where do we now believe that we are? So we need to update the probabilities of what state we think that we are in, and this is how we update that. So let's go through again why this works. Okay, so first, this is now going to be after we've done A and O from the belief B. This is the probability that we now believe that we're in state T. Okay, so first of all, this is after observing O. So if in state T we don't observe O, then we can't be in it, because the probability that we believe that we're in it is going to be 0, because we do observe O. So what happens if in state T we do observe O? So first of all, so let's look at, say that we were in some state S. So this is the probability that we were in S before we performed A and saw O. And this is the probability that from this state S we perform action A and we do indeed reach the state T, and then we sum over all of the states that we could have been in when performing A. So this gives us the probability of reaching T from the belief B when we perform A. So this is the top half of the fraction, and then the bottom half is what we had previously. So this is the probability of observing O after performing action A in our belief B. So we end up with this fraction here, and if you think about this for a minute, we've got a common part to it, which is when we're in B and we perform A, and this is of observing O, and this is reaching T and observing O. So this is the probability of reaching T from B when performing A, and it's conditioned on observing O. So this is indeed the belief reached after we perform A and we observe O. So the final thing that we need, which is much simpler, is the reward that we accumulate after performing action A in belief B. So here, let's look at this. So this is, we were in B, so this is, or we were in the belief B, so this is the probability that we're actually in state S. This is the reward that we would have accumulated if we were in S, and then we sum over all the states that we could have been in. So this does indeed gives us the reward that is accumulated after performing action A in our belief B. So why have I introduced these three things? Well, that's because they're going to be used in performing value iteration over the belief MDP. So this is for an MDP. This was the main step of the value iteration. Okay, now for the belief MDP, we end up with this formula here, which changes slightly. So let's just go through how it changes. So first, whereas for a usual MDP, we base it over our successor states. Now we're doing it over the what we observe, and then we use the reward accumulated after performing action A in our belief B, and then we use this probability of observing O after performing action A in our belief B, and then we use, we're now in this our belief here, so we now look for the value of this our belief, which is the belief that we reach from B after performing A. So we've chosen A from the set and we observed O. So it's the belief that we reach after performing A and observing O. Okay, so this is what we would like to do. Okay, but this is over our beliefs. So this is the set of our distributions over the state space. So that there are uncountably many beliefs. So we obviously can't start to do value iteration over all of them. Okay, so what we can do is resort to our approximate solution of the belief MDP. So we just take our representative set of our beliefs. So let's call them G1 up to Gn, and the one requirement we need is that our convex hull is the full set of our distributions. So there exists our constants, so that if we take a sum using the constants, we can generate any other distribution. And I'll soon show you why we need this. So, which is what this does. Okay, so what we need is interpolation. So given it's like arbitrary belief or a distribution, then we need to find real, it's like constants, let's call them gamma 1 up to gamma n, so that we can write the arbitrary distribution as a sum over these representative beliefs. Okay, and this works because we are required it to be a convex hull. So we can always find these constants gamma 1 up to gamma n. So in the implementation, I'll say a bit more about it's like concrete example of this. Okay, so how can we use these? So it's like what we're going to do is do a value iteration, but just over the our beliefs G1 up to Gn. So let's take one of other grid points, let's say Gi, then so value iteration for this. So this I've just like plugged it into what I showed you before, and what I've also it's like shown you is that we can easily compute this, also this value here, and we can also compute this belief here. Now, and so we also know that O is the set of observations is like finite, and also the set of actions is like finite. So this all looks good. However, this belief here, there is no reason for this to be a grid point. So there's no reason why we know it's our value. So this is the belief reached from a grid point that we know Gi after performing A and observing O. So if O is our target, then it's like we do know it, but if it isn't, then we don't know it's like what the answer is. So now from the interpolation, we know that we have these constants gamma 1 up to gamma n, and we can write GR this our belief using these our gammas, and we do know other values for G1 up to Gn. So we can therefore approximate this the value for this one using these our constants here. Now there's no a reason why this will equal this, so this is an approximation. However, it has been proved that value iteration does converge if we take this approach, and I'll show you also that it also yields sort of upper bounds. So if we find these values, so this will actually converge, then after that, then we can synthesize what I've put in as sort of quotes as optimal, because it's based on these values which are approximate. So that means that it's not actually the optimal, but so I put it in quotes. We can generate a finite memory strategy, so we can step through the POMDP and base our optimal choices on this. So we're in some current belief, and then we can choose some action to perform, and that will update our beliefs. So we'll move somewhere else. How do we choose the optimal value? Well, we use these values that we have. So we approximate the belief that we would have reached. So what happened? So if we do this, then we can generate a DTMC, and we can find out what the values are for this in quotes optimal our strategy. So let's put all this. So it's like before I put this all together, just it's like one thing in it's like practice, what we're not it's like interested in is just it's like saying, well, all of the probabilities are it's like between some it's like minimum or maximum. Okay, that's not really what happens in our practice. What we're usually interested in is just one of it's like the optimal of values. So for example, if you're it's like looking at it's like worst case it's like analysis, then it's like you want to know what's the maximum it's like probability of an error or the expected time or it's like cost. It's not really interested to know what the minimum it's like probability of an error is. But Julie, it's like we want to know what's the minimum it's like probability that a message it's like arrives, or what's the minimum it's like profit of our system. On the other hand, for it's like controller it's like synthesis, it's like we want the dual thing. We want our controller that it's like maximizes that it's like minimizes it's like the probability of an error or the time or it's like cost, or the controller that it's like maximizes it's like the probability that a it's like message it's like arrives. But we don't. But it's like what we're not interested in is that the values are it's like between the minimum and our maximum. So let's go back and put these things together. So let's look at the case for it's like probabilistic it's like reachability. So say that we wanted to know, so these are it's like the actual minimum and our maximum for our POMDP, and we'd be only it's like interested in it's like one of these. Okay, so if we use this grid to do it's like the value it's like iteration, then that gives us an over approximation. So it's like the minimum that we would get from the grid is actually less than or equal to the minimum, the actual our minimum, while the maximum is actually greater than or equal to it's like the actual our maximum. And then we can also synthesize this it's like optimal our strategy. Now this is our strategy of POMDP, so that means that it has to be so our value is greater than or equal to the actual our minimum, and if we've done so the maximum, then it has to be less than or equal to the actual it's like maximum. So this then gives us these two-sided bounds, because as I sort of said, we would only be interested in this case here, or in it's like this case here, and not that it was between the maximum and the minimum here. So by getting these two-sided bounds, we actually get some good if these bounds are it's like relatively tight, then that gives us it's like the information that we need. Now, if the bounds are too coarse, then we can change our grid. So we can try to refine our grid. So add extra our grid points and then try again. Now, since so the problem is undecidable, so we can't guarantee that this will yield it's like tighter bounds. All that we can say is that as the grid goes to infinity, so as we add it, once we add in all other grid points, then we'll get the right answer. So it will converge eventually, but we can't say anything more than that because it's an undecidable problem. Okay, so the final thing before a break, so just to give you something a bit less technical, so let's look at the dining cryptographers problem. So here we've got n cryptographers that are going to share a meal, and the meal's either paid for by the master or one of the cryptographers, and it's the master who decides who pays, and each cryptographer is told sort of in isolation if either the master will pay, or if one of the cryptographers will pay. And the goal is that the cryptographers would like to know if it was either the master that paid or it was one of them selves, but they don't want to know which one of them paid. So Chow came up with a solution. So here it is for 3 cryptographers. So each cryptographer flips a coin. So this is the coin of the first one, this is of the third, and this is of the second. And they only tell their left neighbor the value of the top of the coin. So the first one does tell the third one, but it doesn't tell the second one. So only the third and the first one can see the first, the coin of cryptographer 1. So they look at the 2 coins that they can see. So for example, cryptographer 1 can see its coin and the coin of cryptographer 2. And then if they are paying, then they'll say agree if the coins are the same, and disagree if they're not. On the other hand, if a cryptographer is paying, then it will say the opposite. So it will say disagree if the coins are the same, and agree otherwise. Okay, so it's been proved that this yields a correct solution. So there's a odd number of odd degrees if the master pays, while a even number if a cryptographer paid, while it's anonymity is reserved. Okay, so neither of the non-paying cryptographers or anyone else can find out who actually pays. So just to say that I did do this analysis of this using MDPs, and it did work, but it took 2 to the power n properties using MDPs, and it is a hack. I can say that as I actually did it. While now that we've got POMDPs in Prism, then the model's much easier and more straightforward. And so here, what I've done is that one of our cryptographer guesses who pays after the announcement, when we assume that one of the other n -1 was chosen to pay at random, and obviously now it's not a hack. So let me quickly show you how this works, and then we'll have a slight break. So let me share my actual screen now. So so the first thing, just to quickly show you the model. This is in the Prism language. So we've got that it's a POMDP. Some of the variables of the system can be seen and some can't. So we first got that the master either chooses that the first or the second one pays. And then we've got that each of the cryptographers flips a coin and then does its announcement. And then for the third one, this is the one that is going to guess. So after all the announcements, it then guesses who actually paid. And we've got a property file somewhere. So we're first going to show that so here we've got that it's one of our cryptographers paid, so it should only be an even number of agrees, and then we're going to find out what's the maximum probability that the other cryptographer can guess correctly. So if it is anonymous, then the maximum probability should be 0.5. So let's now actually do this. So we'll first do the first property. So just to sort of say this is, it builds a POMDP, does the grid-based analysis, and then afterwards builds our strategy, and then analyzes the corresponding DTMC. So here we find out that the outer bound is 0.1, and so is the inner bound, so we get the correct answer as the two bounds are the same, and we would get what we would hope that indeed the protocol is are correct. So if we now go on to the second slide, so you won't understand what the grid resolution means now, but you will later. But resolution. So if you start with a very small grid, then we do the analysis, and we don't get very tight bounds. So all that we know now is that the probability is between 0.5 and 0.1. So if we change the resolution, then we can end up with the correct answer. So we know that the answer is between 0.5 and 0.5, therefore it's 0.5. Okay, but since it's an undecidable thing, we can try a different grid, and we can actually end up again with not tight bounds. Okay, so the final thing to say for this one is that we can turn it into a MDP, so we can make everything observable. And if we now find out what's the probability that our cryptographer can guess correctly, well, now it can see everything, so obviously it can guess with probability 1. Okay, so the final thing in our demo, I will go back to the maze example. So this is the maze. So here it can only, it's the robot is initially randomly placed in the maze, and then it can move, but it can only see the observable and not the actual state. So we have these different observables as to which walls it can see. So if we run that now, and we try that with a grid, let's just try something, then we can see that here, we actually get the perfect answer. So let's try it with a smaller one, just to show you that we don't always get the right answer. So here we can see that we only get an approximate result. Okay, and we can do the same thing in that we can turn it into a MDP. So now the robot can see where it is, and if we do it now, then we get a precise result. Okay, so I will now, so I'll stop sharing, and we can now have a break for 5 or 10 minutes.
Yes, are there maybe quick questions that someone would like to ask right now, or?
So I can ask a quick question.
Please, Anna.
Hi. So I see that there is a different time when you compute approximate bounds and an exact solution, and it's always the case that the exact solution, I think, takes longer unless it's an MDP. So can you comment on that? So it's is it easier to compute approximate bounds in terms of?
What do you mean by the approximate?
So you have the exact solution when the bounds correspond to each other, so when they match, and then you have some approximate solution when it's 4.5 and 5.3.
Yeah. No,
and
it isn't always.
It's always shorter in terms of time.
Not always, because I stopped when we got. It's based on the number of grid points. So if there's more grid points, then you've got to compute more values during value iteration. So it will then, take longer for the same, probably for the same problem, but there's no guarantee, because it's all on also the convergence, how it converges. So it's both dependent on the number of grid points and what the grid points are, and are they close to the beliefs that you actually it's like want to be in. And as I'll say, it's like towards the end, it's sort of, this is quite a, it's like naive, it's like approach where you just fix the grid points. But if
this was my concern. This was my concern that it's probably very dispersed in how fast it goes when it's approximate solution. And can it be the case that if we have a certain belief, we can actually stop at some point and say, okay, we're happy with this approximate solution and we are not going to explore anymore other beliefs, for example, or the rest of the grid or something?
So you need to do it for all of the, it's like states. It could be that some aren't, it's like reachable, so they're not used. So
so I can in principle throw them away and just say, okay, I'm happy with this one.
Yeah, and that is what we actually do in our practice. So we look to see if it's actually, it's like used, and if it isn't, then we don't. But it is very naive. It's like we haven't really had a chance to go on to sort of, it's like optimizing this, which is one of the reasons that I've focused on this as it's work that I would like to take forward. So.
Okay, thanks.
Okay, maybe let's take a break until, for next 6 minutes. So we start at 45, whatever is your time zone, so that we also get in a chance to get a cup of coffee. And
Okay, great, thank you.
Thank you. Great tutorial. Thank you very much, Gethin. It's really exciting and interesting. Can I ask one question while it's actually more like understanding question. It is when you compute beliefs, are you always guaranteed to converge on the values?
Using the grid-based, yes. It's been luckily someone in the past proved that these are converge, and that they converge to over approximations. So okay, it's very involved, the proof, to say the least. So.
Okay, I was just wondering because like it wasn't very intuitive, but okay, if you say it's very involved proof, that it's understanding when someone who is not in this field, it's not intuitive why you will be able to compute. But yeah, thank you.
Okay.
So it looks that everyone is back. So shall we continue then with the second part of your tutorial?
Yeah, sure. Okay. Okay, so in the first part, it was all about a discrete model of time. So here, what I'm going to do is move to a dense or continuous model of time. So let me just get it to check. Okay, so first, so as I said, so we're now going to have a dense time our domain. So we're going to take the non-negative reals. So our time now is over the non-negative reals, and we'll assume that we've got a finite set of clocks that we'll call x, and each clock, little x, is a variable that takes time value. So they're values from our time, our domain, and we will assume that all clocks increase at the same rate as real time, so they act like clocks. And we also assume that we can set them, so we can set them to 0. And what a clock evaluation does is it just tells us what's the value of all of the clocks at a current time point. Okay, so it's just a vector over the clocks. Okay, and then if some time passes, then obviously all of the clocks should increase by that time. So if the clock evaluation was v and t time units pass, then we should move to this clock evaluation here, v plus t. So for each clock x, our value was what it was, so v of x, and then t time units have passed, so the clock increases by t time units. What we also need are zones over clocks. So these I will denote by zones of x. So these we can consider as a subclass of polyhedra. So these are when these gives us our conditions when all the clocks are in satisfy certain our constraints, then we can do certain things, or we can't do our certain things. So we can say that a clock is less than or equal to some integer value, or it's greater than or equal to some integer value. We can compare the clocks, we can take our negations, and we can add these clock constraints or zones. So we can say clock x is less than or equal to 4, and clock y is greater than or equal to 7. Okay, and then we say that a clock evaluation satisfies a zone is if the zone is true after for each x we substitute in the actual value from the clock evaluation v. Okay, so we can now use these concepts to introduce probabilistic timed automata. So these, you can either think of these as MDPs plus real valued clocks, or you can think of them as timed automata plus discrete probabilistic choices. Okay, and so this gives us now a model that has probabilistic, non-deterministic, and now sort of real-time behavior. So what is a PTA? So at first it looks a bit complicated. It's quite a long tuple. So let's go through what each part is. So first we've got a finite set of our locations. So these are sort of, you can think of these as sort of the current state absent of what our clock our values are. So we've got a finite set of our locations, and we start in some initial our location L/0. We've then got, as for MDPs, we've got a set of actions that we can perform, and we've also got clocks. So a actual state is now our location that we're in, but also it also says the value of all the clocks X. So it's our location plus a clock valuation. And then we have these three different functions. So first we have a invariant condition. So this says what the values of the clocks have to be in a certain location. So so it goes from our locations to zones or clock constraints. So that says the condition on what the clocks have to satisfy to be in our location. Then we have a enabling function. So this says if I'm in our location, can I currently perform a given action? So given a location and action, then it returns a clock constraint or zone that says what has to be satisfied in order for that action to be taken. And then we've got a probabilistic transition function. So this says if I'm in a location and I can perform an action and I do, then this tells me the probability that I reset some set of clocks and I move to some other location. And finally, we've got a reward structure, which both gives us a reward over our locations and a reward over the actions. And I will come back to how these work. So let's just first give you a very simple example to give you sort of more understanding. So here's a simple probabilistic communication protocol. So we start in some location DI. So in the initial location, we start with all the clocks equal to 0. So say that, let's start with that we've just got a clock X. So now if we look, then we've got an invariant for our location DI that says that X has to be less than or equal to 2. So it's we have to leave DI before X is greater than 2, and X is a clock, so it increases at the same rate as real time. So we have to leave it after by the time that 2 time units have passed. And then we've got this one action, which is send, and we can only take this after X is greater than or equal to 1. So if we combine the invariant and the guard, then it follows that we have to take the send action between 1 and 2 time units. So after we do the send action, then with probability 0.9, we'll move to the our location SR, and I haven't put any clocks that are reset here. So we just move to this our location, and X would keep the same value that it had previously. On the other hand, with probability point 0.1, then we move to our location SI, and we reset the clock X. So we'd move to SI, and the clock X would now take value 0, and then it would start to increase again from 0 at the same rate as real our time. So if we now also look at SI, so here we have the invariant X is less than or equal to 3, and the guard, the enabling condition X is greater than or equal to 2. So this means in SI, it's between 2 and 3 time our units, we attempt to retry, and we either go to SR, or with probability 0.05, we would go back to SI, X would get reset, and then we would do the same thing over. So if we failed, then we try again, between 2 or 3, and if we fail again, then we try again, between 2 or 3 times our units, and so on. Okay, so just one extra thing to say here is that if we added an extra clock here, Y, so here it would start from 0 here, and if we didn't reset it on either of these, then this would, and we put this extra our condition here on the enabling our condition, then we could only take this retry in the case that less than 10 time units had elapsed since the system started. Okay, so that's just to show you that there's more going on than just having this one clock X. Right, so that's intuition. So let's now give the formal our semantics, which is an infinite state MDP. So here, as I've said, the states of the MDP give our location and then a valuation to the clock. So it's our location clock valuation pair, and it has to be such that the invariant of our location is satisfied by the clock of valuation, because we can only be in that location when this invariant are satisfied. And the initial state of the MDP is just the initial location with all the clocks set to 0. And what are the actions? Well, here they are time and actions from the PTA, so they're pairs of the form TA. So we let some time pass, and then we perform some action A. And we need some, obviously there's some requirements on it, given that we've got invariants and guards, and we need to follow the probabilistic transition function. So first, if we were in state LV, then we can choose a time T and an action A, and we have our non-deterministic choice over this, and this can be over an infinite set of time action pairs, as time is over the reals. And we require, first of all, that while time passes, the invariant remains satisfied. So it's continuously satisfied during time T. So the valuation plus T prime satisfies the invariant for all T prime between 0 and T. Then we need to be able to take A. So that means that we need A to be enabled after the T time units have passed. So it has to satisfy that. So V plus T has to satisfy the enabling our condition, given that I'm in L and I'm trying to perform A, and then finally, we need to satisfy the probabilistic transition function. So that means if we choose A, then the probability of moving to our location L prime and resetting some set of clocks Y, then this is given by the probabilistic transition function. So just to show you a example execution. So if we resolve all of other non-determinism, then we're going to get our DTMC. So we start with the clock X equal to 0. We could choose to let 1.1 time units pass, then do send. So we would first move here, and then X would be equal to 1 plus 1, and then we would do the send. So we'd either end up in SR, and X would be 1.1 because we don't reset X, or we'd move to SI, and X would be equal to 0, since we do reset it here. And then in SR, we might choose to let some time pass, and here it can be any amount of time greater than or equal to 1. So we choose 8.66, then we would set X. X would then be 0 because we do reset, and we've got a similar thing here. So that's just to show you how it works. So finally, on our semantics, how do the rewards here? Well, we have two different rewards. We have our location rewards, and these are as time, the more time that passes, the more that these accumulate. So our location reward says the rate at which the reward is accumulated. So if we spent time t in our location L, then it would be this value times t. That would be the reward that we would actually accumulate. And then the action, our rewards, they are instantaneous. So they just if I'm in our location L and I perform A, then I get this instantaneous reward. So I'll just mention that these, this is actually the probabilistic extension of what are called linearly priced timed automaton, which are also called weighted timed automaton. Okay, so that's the general our semantics, but we've got an issue in that in our state space are countable. Okay, the states are clock, our valuation pairs LV, and V is over real our values. However, we could consider just the digital clocks are semantics. So this is where digital clocks mean what you would think. They can only take integer or digital value. So this means that we changed the time, our domain, from the reals to a subset of our naturals. And what's been shown is that the digital clocks semantics yields a finite state MDP, which preserves both optimal probabilistic and expected reachability our values under the requirement that all the zones are closed. So there's no strict inequalities, and you can't compare clocks. So all of the our components in the zone are either a clock X greater than or equal to some value, or less than or equal to some value. In both cases, the value has to be an integer. And we don't need to take the full set of our naturals, is that we can bind the clocks by Kmax plus 1, where this is the maximum constant that is in the PTA. So if we do this, then we get a finite state MDP, and then we can use the analysis, our techniques that I introduced earlier. And if it's closed and are diagonal free, then we actually get the correct values for our PTA under its sort of original semantics over the reals. And if we take this approach, then automatic analysis of our PTAs exists. So we can give our PTA, our specification. If it's closed and are diagonal free, then it can use this, so create a finite state MDP, do the analysis, and return the correct optimal probabilistic or reachability of values. So these might sound like quite strong restrictions, but in practice, we've seen that there are many case studies that fit this. But it can lead to, if this K max is large, it can lead to large MDPs, but Prism has a sort of a symbolic engine, and we've been able to analyze MDPs with hundreds of or millions of states using this approach. Okay, so I'll just mention that there are alternatives for analyzing our PTAs. So there's what's called the region graph, which is useful for proving our decidability results, but it's exponential in size, so it isn't useful in practice. And then we've developed a number of zone-based approaches where you sort of take the PTA and then you build a finite state MDP by sort of traversing through the PTA, and you build the states of the MDP and then our location and zone pairs. So it's sort of a symbolic state that represents all of our location clock valuation pairs where the valuation satisfies the zone. So there's a number of approaches. So the first was using forward reachability, and this gave only a upper bounds on maximum reachability probabilities. We since extended that to allow optimal reachability probabilities. So this is both minimum and maximum reachability probabilities, and this was through a game-based abstraction and refinement approach, but it does introduce what are called non-convex zones, which means that it can slow it down in practice. There's also the dual approach based on backwards reachability, and here you can compute optimal both probabilities and expected rewards. For rewards and the minimum case, it does again we get non-convex zones which can slow things down, and for our rewards we also need to move from integer constants in the zones to rational ones, which obviously means that it's going to be of less use in practice. So that's just to say that there are these ones there, and if you're interested, I can give you more details on these. So finally, onto partially observable PTAs. So here we've got an even longer tuple, but the first part is just our PTA that we've already seen, and all that's new is that we now have a set of observations and then a function that says if I'm in our location, what can I observe? So it's like for our POMDP, but here it isn't what can I observe when I'm in a state, it's what I can observe when I'm in our location. And similarly to our POM-DPs, if two our locations are observably the same, then they have to have the same invariance and enabling conditions for all actions, as otherwise they wouldn't be. Our strategy could tell them apart. Okay, so under this we get a uncountably infinite state POM-DP as our semantics. So the transition and reward functions are as I gave for PTAs, and for the observations, if I'm in a state of which is a location clock valuation pair, then I observe what I observe of our location, and I get to see all the clocks. Okay, so notice all clocks are visible. Now you could, or we have started to, or we did start to consider the case where some of the clocks are hidden, but that makes things even more complicated, as you would need sort of a second player to deal with these other clocks, and then you'd have to move to partially observable two-player games, which are even harder to solve than POM-DPs. Now, what we've shown is that under the following restrictions, then the digital clocks semantics preserves the probabilistic and expected reachability values of a partially observable PTA. So the zones have to be closed and diagonal free. So that's the same as PTAs and for timed automata. And then we also need that resets can only be applied to clocks that are non-zero. Why is this needed? Well, otherwise clock resets can be used to differentiate between our locations. So say that we had probabilistic edges going to two observably equivalent our locations, where only one of the edges reset a clock, which we can obviously see. Then if we had real valued clocks, then our strategy could be able to tell our difference at essentially no cost. It could let an arbitrary small amount of time pass so that a clock was greater than a zero, and then if it took the transition, then it could tell the difference between the two locations. While in our digital clocks, you would have to let either zero or 1 time unit pass. If it was zero, that wouldn't help you to differentiate. So for the real valued and the digital clocks to be equivalent, you need this our condition here. But so just to say that both of these are easy to check syntactically on our PTA. So we have our semantics of a partially observable. Our PTA is a infinite state of POM-DP. We can then use the digital clocks. If our conditions are true, then we can construct an essentially equivalent finite state POM-DP, and then we can use our techniques from the first half of the talk and get upper and our lower bounds, and also do our refinement of the grid if we wanted to. Okay, I'll finally quickly mention sort of implementation, but given the time, I'll skip the case studies. Okay, so just to say that this is now part of the main branch of our Prism now, so you can now do the analysis of both our POMDPs and partially observable our PTAs using these our methods. And it's like the Google's summer of code was used. There was a intern that did some of this. And just to say how this works is that we have this fixed grid from other literature that's very naive. So it's given, so this is the grid of resolution that I was using when I was running Prism. So you just set you choose your M, and then this gives you these grid points here. And our benefit, or why we chose to do that, is then it's easy or easy-ish to find other constants, gamma 1 up to gamma n, given any arbitrary belief. And this is, as I showed you, that this was needed during value iteration. And our downside, as well as this being our naive approach, is also if you increase m, then the grid points grow sort of exponentially. And we could certainly try to improve the efficiency with more complex grids, and trying to vary them based on the beliefs that we actually encounter during value iteration. Okay, so I'll skip the case studies, and I'll conclude. So what I've introduced are models that have non-determinism, real-time, probability, and partial observability. And at the start, I tried to motivate that these are required for many real-world case studies. And there's a lot that we could do to improve things. So as I've said, we've only presented a very simple solution method, and there's many more advanced techniques for finding different values that we could probably try to adapt to here. For the real-time side, we used the digital clocks, semantics. We could look into using symbolic techniques, both in terms of our BDDs and in terms of the zones, and zones have proved to be more efficient than digital clocks in many cases. And obviously, one big limitation is that all the clocks are observable. So it would be good to move to a case where some of them weren't. But and there has been some work on this in the non-probabilistic case. So this is for time automata, partially observable timed automata, but you would have to move to games, and as I've said, things get more complicated there. Okay, so I'll finish then, and I'll open up to any questions.
Thank you very much for the very nice tutorial, Gethin.
Thank you.
Let me first open the floor for some questions if someone has. You can type them or raise hand. And if not, maybe then I will do something that I actually would really like to know more about case studies. If you could, you don't really need to go through them, everyone, I can see nodding, everyone would. If you don't need to go through all the details, but maybe just give us a flavor of, on which properties did you prove out for the real world systems. And
okay, I can.
But that's why I said, if there's some questions, please shout, because I would really like to know case studies.
Okay, so there's one that was sort of based on our wireless, our scheduling of our packets. So here, it's like you can't tell, it's like the state of our channels, because if you did try to find them out, then that would slow things down, and it comes at a cost. So we looked at sort of what was the maximum number, sort of how to minimize the number of packets that were dropped, or to maximize a reward, and our reward was sort of based on the number of our packets sent, but also some of the packets had higher priority, so they had a higher reward. So we looked at.
Excuse me, can I ask? Did you have some probabilistic or stochastic requirement at which rate the packets are coming in, or was it?
Yeah, so we set, so it was our probabilistic as to if a packet would come in at each sort of at the beginning of each time slot, and also it was our probabilistic as to if it was a low or medium or high packet. Mm-hmm. And then also the behavior of either channel was our probabilistic, so it could sort of like go down, or sort of, so that it wasn't always operational. But what we found was some of the time it was good to not actually send anything, and just to watch to see what our state our channels were in, and then you can use that to make sure that the high our priority our packets do get sent, which obviously therefore gives you a bigger reward, and you might lose out on some of the lower ones. So that was one of the case studies. It's like the second one was when a person was, so there was sort of, there's two people, one was high and one was sort of high our security, and one was low, and the high person was trying to get a secret to the low person just by delaying messages, but to try to stop this, it was put through a buffer. So as things came in to be sent, then there'd be sort of then a random delay would be added to them to try and hide, or to try and stop high from transmitting this. So it was to see how effective this was. So could low guess the value after seeing the our delays that had been sort of randomized. So obviously, if you add in a really big delay, then even if you add in more time, sort of if you try to add in sort of a probabilistic part to the short one, then you have to add in a huge delay to sort of hide the fact. So does that make sense for that one? And then there were two other ones. One was sort of task or scheduling, and so you couldn't see if a process was sleeping or just idling, because if you wake it up from sleep, then that is a much bigger cost than if it was idling. And then the final one was a repudiation protocol. So here you've got sort of the recipient is trying to get some information from the originator, but it can't see it all until it's all been sent. So it's fair to both our parties. And this needs both timing and probabilistic values.
Okay, thank you for showing this. And are there more questions that think that really kind of gave us also better feeling about the properties that can be proven, the systems that can be modeled. More questions? Oh, Raina, sorry, you have a hands up, please.
Yes, I have a question about the type of so in the case studies that you considered. Did you have situations where it was unnatural to assume that clocks are observable and you had to model around that, or?
No, but it's hard to know, because I knew that clocks were observable when I was choosing which case studies I was going to look at. So there are certainly cases where you'd want the clocks to be hidden, but there's also cases where it's really not a problem. So
so in the case that you consider, you didn't have to
no.
didn't have to kind of model around it or make unrealistic assumptions.
Yeah. But it would be great to be able to do that, because it would certainly add something new. So.
And in terms of the other restrictions that you had on the shape of the automata of the,
they didn't. That wasn't an issue. So.
And if I may ask one more question, so about so you mentioned about kind of more sophisticated approaches for choosing these representative beliefs. So is there already some kind of like good heuristics that are being employed, or it's still?
There are in other planning and AI worlds, but it's sort of in. But there they've got a different problem, because there they either look at sort of they have a fixed time bound, and if you think about that, then you're only going to encounter finitely many beliefs if you only do finitely many states, and then all the issues about undecidability go away. Whereas in the verification sort of community, so most of the time we seem to be so the focus is on sort of unbounded or properties, and there are different, but there are certain things from there which I think can be used to help, because it seems clear that this grid-based thing, it's only if the beliefs that you want are close to the grid points, then it can work well. But if they're far away, then it doesn't work well. So if you can choose your grid points so they're close to the beliefs that you see, then, or you see with a high probability, more importantly, I think, then that can really help.
I mean, I guess another difference is that in planning, oftentimes you have, like some kind of numerical reward, while like from a verification perspective, you might have your property expressed on a higher level that you have compiled down to a reward. And that might help in terms of kind of doing some analysis from the point of view of verification techniques, identifying what would be a good.
Yeah.
I don't know.
Okay.
Thanks.
Okay.
I have to stop here because we are out of time, and I know that we are all in different time zones. So I want to really thank you. Well, I see we have Suprati, who is in India, whom is right now middle of the night. So we have to stick to the schedule. So thank you very much once more, Gethin, for this really nice and informative tutorial. It was very interesting for all of us, and I'll see you all tomorrow. So thank you once again. Thank you.
Okay, thanks a lot.
Thank you. Bye, everyone. Bye-bye.